the talk is on the pentagram map and the integrability property of such map. So I'm happy to present you Anton Izosimov.
Okay, thanks. How much time do I have?
So as you like, 1 hour, 1 hour and a half, as you like.
Okay, okay. We'll see how it goes then. Can probably do it in an hour, maybe an hour and a bit. Okay, so I have to say I'm sorry because it seems that some of you have heard the talk before, but Dima asked me to give this talk once again, so I suppose I can do that. So I'll indeed talk about some things related to the pentagram map, even though the problem I'll discuss, it's a kind of a more geometric problem. So let me start with some very classical stuff, which goes back to 19th century. Namely, let's consider a pentagon in the plane. So it's gonna be a pentagon, and having such a thing, we can draw all the diagonals of this pentagon. And if we do that, then we obtain a new pentagon in the middle. So its vertices are just the intersection points of the diagonals of the initial one. And well, one may ask if this new pentagon is somehow related to the initial one, and it turns out that it's indeed the case, and it's a result that's apparently due to Clebsch. It could have been known earlier though, but this can be found in some paper by Clebsch. And what this theorem of Clebsch is saying, that this initial pentagon, which we call P, and the new one, they're projectively equivalent to each other. So there is a projective there is always a projective transformation that's taking P to P prime. And note that, well, it's a non-trivial statement because the space of pentagons in the plane is 10-dimensional, and the projective group has dimension 8, which means that there is a 2-dimensional space of equivalence classes of pentagons. Not all pentagons are the same from the projective point of view, but nevertheless, it turns out that P and P prime, they always represent the same projective equivalence class. And this can be made a little bit more precise, because when we say that there is a projective transformation taking P to P prime, we should specify which vertex goes to which vertex. And here we label the vertices 1, 2, 3, 4, 5. Then the vertices of P prime should be labeled in the following way, that the vertex 1 of P prime should be directly opposite to the first vertex of P. So this is going to be 1, this is going to be 2, this is going to be 3, this is 4, this is 5. And notice that this is kind of the only way to label P prime in a symmetric fashion. So any other labeling would break the left-right symmetry, but this labeling is the kind of the most natural one. And what this theorem of Clebsch is saying, that there is a projective transformation. Oh, maybe let's call this 1 prime, 2 prime, 3 prime, 4 prime, 5 prime. There is a projective transformation phi, which takes each vertex I of P to the corresponding vertex I prime of P prime. Okay, so, and this is very easy to prove, of course. One needs, there is a completely geometric proof. One needs to extend certain sides, compute certain cross ratios. It's a nice exercise for undergraduate students who take a course in projective geometry. It's a pretty straightforward synthetic proof. And or of course there is a computational proof too. So this statement is not hard. So this this is a result on pentagons. And now we're going to talk about the generalization of this to more general polygons. And here we'll follow the work of R.Schwartz. And this was 2000 something, I don't remember, 2003, 2005, so a few years ago. So he considered the generalization of this to more general polygons. And while it's clear that in general such a result is not true for arbitrary polygons, if we consider an absolutely arbitrary polygon, we draw its diagonals, we take the intersection points, okay, we get a new polygon. There is no way it's going to be projectively equivalent to the initial one. This is completely not true, but it turns out that it is true for a particular class of polygons, which can be viewed as a generalization of pentagons, and those are known as Poncelet polygons. So Poncelet property is the property that this polygon admits an inscribed conic and also a circumscribed conic. So if we are thinking about a convex polygon, then this means that you can inscribe an ellipse in this polygon, and you can also circumscribe another ellipse around this polygon. So the polygon should be such that, well, its sides touch a certain ellipse, and there is also an ellipse containing all the vertices. And it's clear that all pentagons have this property just because for any 5 points there is a conic through those 5 points, and for any 5 lines there is a conic touching those 5 lines. So all pentagons have the Poncelet property, but starting from hexagons, that's a non-trivial condition, because if we have arbitrary 6 points, well, there is not going to be a conic through those 6 points, and if we consider the sides, there is not going to be a conic that's touching those sides. So that's actually a very restrictive condition. And as we saw, the space of pentagons, it's 2-dimensional if we consider pentagons up to the action of the projective group. And one can show that for any number of vertices, actually the space of Poncelet polygons, it has the same dimension. So the space of all polygons, it becomes huge. But the space of Poncelet polygons, if we identify those that are projectively equivalent, it's a 2-dimensional space. And what Schwartz proved, well, he proved that exactly the same result as what I started with, this Clebsch result. It also holds for Poncelet polygons. Namely, what we should consider a Poncelet polygon P. And we will assume that it has an odd number of vertices, because remember, we had this special labeling of the polygon P prime. And for that special labeling to exist, we need to have an odd number of vertices. Otherwise, we just don't know how to label the vertices of this new polygon we obtain. So we have a Poncelet polygon P with odd number of vertices. And then we just repeat exactly the same construction. Well, of course, this needs to be clarified a little bit, just because for polygons with number of vertices more than 5, there are just too many diagonals to form a new polygon. 1, 2, 3, 4, 5, 6, 7. So here is a heptagon. So what we do for more general polygons, if we consider all the diagonals, there's going to be too many. So instead of considering all diagonals, we consider what's called the shortest diagonal. So these are just diagonals connecting second nearest vertices. So we do intersect all those diagonals connecting second nearest vertices. And then if we do that, then we again obtain a polygon with the same number of vertices as the initial one. So this is P. We get a new polygon that we call P prime. And we also know how to label that new polygon. So here is a vertex that's 1. This is the opposite side for that vertex. Well, if I got the number of vertices correctly, of course. But basically, we look at the opposite side, and there is a vertex of the new polygon that's adjacent to this opposite side, and that we call 1 prime. And then we label all vertices in the same way. And this is something that can be done only for odd number of vertices, simply because for even number, there is no notion of opposite side. It doesn't make sense. So, and what Schwartz proved is that if P is such a Poncelet, so we assume here in this picture that P is a Poncelet polygon, has odd number of vertices, we form this polygon P prime, and then Schwartz proved that P and P prime, they are projectively equivalent to each other. And there is actually a version of this result for odd number of vertices too, namely, for even. In the even case, it turns out that P prime is projectively equivalent to the dual of the polygon P. But in this talk, we'll only be interested in polygons with odd number of vertices. This is the case when this result is a kind of the most simple and the most natural one. So this theorem of Schwartz is a natural generalization of Clebsch's result. So provided that we regard these Poncelet polygons as some kind of generalized pentagon. And well, the problem I was interested in is some kind of an inverse problem for this one. So namely, well, assume that we have a polygon P with an odd number of vertices, and then we can form this polygon P prime, whose vertices are the intersection points of shortest diagonals of P. And let's assume that we know that P is projectively equivalent to P prime. So we have a polygon which is projectively equivalent to the polygon formed by this intersection points of diagonals. So in this case, is it true that it should be that P is a Poncelet polygon? And of course, if P is Poncelet, then P prime is also Poncelet, because we assume that they're projectively equivalent. And well, it turns out that this is not true without any additional restrictions. And hopefully it will be clear later where those come from. But what I prove is that, well, if we assume this property that P is projectively equivalent to P prime, and in addition, we need to assume that, well, first of all, of course, this question makes sense over any field, because all these notions are defined over any field. In particular, we can do it over complex numbers or over real numbers. Then over complex numbers, it's not true. Over complex numbers, one can construct a simple counterexample when this is not true. So we will assume that P is a real polygon. And moreover, we'll need to assume that it's not just real, but it's also a convex polygon. So it turns out that if P is real and convex, and it has this property that it's projectively equivalent to its, so to say, diagonal polygon P prime, then this completely characterizes Poncelet polygons. So this can be viewed basically as another definition of Poncelet. Instead of requiring that there is a circumscribed conic and inscribed conic, we can say that, okay, that's the same as being projectively equivalent to this diagonal polygons, but provided that it's real and convex. And well, this sounds as a kind of a simple geometric theorem. I'm not aware of any elementary geometric proof of that. Maybe there is a completely elementary geometric argument, but apparently such an argument, well, at least it's not completely straightforward just because of these restrictions. Because if there was an argument along the lines of classical projective geometry, then apparently that would work for complex polygons as well. But this is just not true for complex polygons. So but still maybe there is an elementary proof. And today I will present a proof of this, which is, well, pretty much based on the theory of integrable systems, and it's kind of not elementary at all. But maybe after the talk you will tell me that there is an easy proof, and I'll be happy to hear that in that. So first of all, before I start discussing the proof, let me say what this has to do with integrable systems. Well, there is an integrable system drawn in this picture. Namely, well, here we are considering the situation when P is projectively equivalent to P prime, but of course we can do it for any polygon P, and then we can just regard this as a dynamical system. We can look at the map which sends P to P prime, and this makes sense for any polygon, or at least for any generic polygon, because, well, if a polygon P is sufficiently bad, it may happen that we're not able to define P prime. So it's clear that actually, well, if you try to compute the coordinates of vertices of P prime, that those will be given by some rational function. So the map sending P to P prime is actually a birational map. So it's generically defined. And also notice that this map is projectively invariant, because in the definition of this map, the only thing we do is we intersect straight lines. So this map commutes with all projective transformations. And because of that, it's natural to consider this map, which sends P to P prime, on space of polygons modulo the action of the projective group PGL3, and it's, well, it's a well-defined mapping on this space of projectively equivalent classes of polygons to itself, and it can also be shown that it's a birational mapping of that space to itself. And in this setting, this has a name of the pentagram map. So the pentagram map, it's not the map on polygons themselves, but it's a map on projective equivalence classes. It's clear why this should be so, because, well, what I want to say is that it's an integrable map. But if we regard this map as a map on polygons, it's clear that it cannot be integrable, because when we apply the map, well, P prime is clearly smaller than P. And if we start to iterate this, then the polygon will be becoming smaller and smaller, and this doesn't look as integrable dynamics at all. Well, at least it's not quasi-periodic for sure. Maybe it's integrable, but, well, then the level sets in this integrable system, they're not compact, because it's not quasi-periodic dynamics. But what we need to do is we need to mod out this action of the projective group, and then we no longer have this problem that the polygon is becoming smaller because the size does not make sense anymore. Basically, now we're just looking at the shape of the polygon from the point of view of the action of the projective group. And then it turns out that this pentagram map, it's a discrete integrable system. So it's a discrete integrable system. So this map, it was actually, well, it was in some form considered by classics in the 19th century. I already quoted this result by Clebsch. So the serious study of this began in 1991, I think. So Schwartz wrote a paper about this, and he observed that it does have some properties which resemble integrable dynamics. But integrability of this was actually established in 2010 in a paper by Schwartz and with Ovsienko and Tabachnikov. So they proved that this is indeed an integrable system. And after that, this map actually became very popular. So now there are dozens of papers written on this. And, well, the reason for that is that it turned out that it's connected with a lot of other topics in the field of integrable systems, but also in combinatorics. In particular, well, this map is now a standard example of what is called a cluster integrable system. So it's connected with cluster algebras. So I won't say much about this, but let me just briefly explain what, well, probably you know better what a cluster integrable system is than I do. But the basic idea is that, okay, so in cluster algebras, you can describe them by quivers. So you have these graphs and you have variables attached to vertices of the graphs. And then you can mutate any vertex. And when you mutate any vertex, you change the variables, but you also change the graph. And when you have a graph, to this graph, you can also usually associate a Poisson structure. And this Poisson structure, it changes when the graph changes. But it may happen that if you mutate several vertices one after another, then the graph kind of comes back. So it becomes the same as it initially was. And this means that the Poisson structure is also the same. So when we compose several mutations, we get a Poisson map from the initial space to itself. And there are many, and well, yeah, we have, and the map itself is a composition of these mutations. And well, there are, of course, this doesn't yet provide any integrability. It's not clear why this should be an integrable map. And in general, it's not the case. So one needs some additional structures to prove integrability of this. Well, basically, those constructions are usually related to some embeddings of this quiver into a torus, for example. But having these additional structures, this map that we obtain, it also has some number of first integrals, and it may turn out to be an integrable system. And the pentagram map is exactly of this kind. So this was initially observed by Max Glick, that this can be represented as a sequence of mutations corresponding to a certain quiver. Later, there was this huge paper by Goncharov and Kenyon, where they introduced a large class of such systems. And it was also observed that the pentagram map fits into that construction. And there were several other results, different general constructions of cluster type integrable systems. And well, the pentagram map turns out to be like one of the most natural example, and it fits in most of this constructions. Okay, so now any questions up to this point? So now returning to our initial problem, so we wanted to study the problem when this P and P prime are projectively equivalent. So in terms of the pentagram map, this kind of means that P and P prime are the same, because we consider the map on the space of projective equivalence classes. So in other words, what we want to study fixed points of the pentagram map, and we can reformulate our question as a question of describing the fixed points of the pentagram map. So it should be already clear by this point that, well, this has something to do with integrable systems, because we are describing fixed points of a certain integrable system, and hopefully we can use techniques from integrable system to answer this question. Okay, so now let me start explaining my approach to the proof of this result. Well, before I do that, I should say a little bit more about Poncelet Polygons. So Poncelet Polygons, well, so these polygons were considered by Poncelet in the beginning of 19th century, and recall that, well, the Poncelet polygons, there is an alternative description of them. So they can be described using the following construction. So let's take two conics, one inside another, and let's take a point on the outer conic. And from that point, we draw one of the tangent lines to the inner conic. And then we repeat this construction once again and repeat it many times. And then, it may happen that after this is repeated many times, then this polygonal line, it closes up. Well, it doesn't quite happen in this picture, I guess. it's actually hard to choose an initial condition in such a way that it closes up, and that condition it's quite transcendental. But well, clearly it may happen that after some number of iterations, well, maybe now it's closed up. So after some number of iterations, this may close up, and in this case, what we obtain is exactly a Poncelet polygon, because by construction, this polygon is inscribed in this outer ellipse, and it's circumscribed about the inner ellipse. And a famous theorem by Poncelet says that if we take the same, well, let's assume that it closed up after n iterations, and let's take the same two conics and start doing this procedure, but from a different point, then the theorem due to Poncelet is saying that, okay, it's gonna close up again. If we start from a different point, no matter what initial point we take, if it closed up after n iterations, then starting from a different point, that's gonna happen again. It still will close up after n iterations, well, possibly less. If n is not a prime number, well, say if n is 6, it could close up after 3 iterations. But that's also fine, because if it closes up after 3 iterations, it will also close up after 6. So it will close up after the same number of iterations. This is Poncelet theorem, and that's basically why people study this Poncelet polygons. It's something related to this Poncelet theorem. And let me explain just in a couple of words how one can prove Poncelet's theorem, because this will play a role in what we'll be discussing today. And well, from the modern point of view, this proof is completely elementary. There exist very many different proofs, so I'll provide a simple argument for why Poncelet theorem is true. Namely, well, let's consider the following space. So let's fix this two conics, and let's consider the space that consists of flags of the following form. One element of the flag will be a point in the outer conic, and the other element of the flag is a straight line passing through that point and tangent to the inner conic. So we consider this space, and well, this space, clearly if we fix this point, then generically there is two tangent lines through that point, and that means that the space of flags that we consider, well, there is a projection from that space to the outer conic. It just sends the flag to the point on the outer conic. So there is a projection from this flag to the outer conic, and this outer conic, of course, is, well, if we consider it in CP2, then it's P1. So there is a projection from flags to P1, and this projection is a 2-to-1 covering, but it's only 2-to-1 covering generically, because there do exist points on the outer conic from which there is only one tangent. And we don't see these points in this picture because those are actually intersection points of the two conics. So if we pick an intersection point, then there will be only one tangent line from that intersection point. And well, in the complex projective space, there is always 4 of them, counting with multiplicity. So this is a 2-to-1 covering with 4 branch points. And then from this, it follows that this space of flags, it's an elliptic curve, just by simple count using Riemann-Hurwitz theorem. So the space of flags it's an elliptic curve. And then, well, there is a simple description of what our map is. Well, there is this Poncelet iteration. When we draw this tangent line, we find this next intersection point, and then we repeat this procedure. So what this map is in terms of our space of flags, well, we can regard it as a composition of 2 maps. So one map does the following. It takes this flag and sends it to this flag. So it's the same tangent, but opposite intersection point. And it's clear that this map is an involution. If we repeat it twice, we get what we started with. So we have this involution, And then we have another involution. That's the involution interchanging these two tangent lines. And the map we are interested in, it's a composition of those two involutions. And well, then for any elliptic curve, we have an elliptic curve and we have an involution of that elliptic curve to itself. It always has the form x goes to c minus x, where this subtraction is in terms of the natural addition structure on the elliptic curve. And if we compose two maps of this form, then what we'll get is we'll always get a shift. So it follows that the composition of two involutions on an elliptic curve is always a shift. So our map is a shift on the elliptic curve, and so it's of the form x goes to x plus a, and by construction a does not depend on the starting point. A just depends on, well, what these two involutions are, and because it's a shift, and well, if it closes up after n iterations, this means that a is an order n point on that elliptic curve, in which case it's clearly gonna close up after n iterations regardless of what the starting point is, just because a is an order n point. So it doesn't matter what x is. So you pick x, any x0, then you add a n times. Well, if a is an order n point, it's gonna be x0 again, and that proves Poncelet's theorem. Okay, so what we see from this construction, well, of course, it's a very well known proof why I provided it. So what I wanted to explain is that, well, basically the Spectral Polygons, they're closely related to elliptic curves. As one can see from this proof, well, basically a Spectral Polygon can be constructed from a certain set of data, and this data is basically an elliptic curve and an order n point on that curve. If we have this data, then one can explicitly construct a Poncelet polygon based on that data. One can find explicit formulas of vertices of that polygon in terms of that data. It will be given, the coordinates of vertices will be given by some elliptic, the values of some elliptic functions associated with that curve, and that, oh, well, this point of order n will also play a certain role in the formula. So basically, Poncelet polygons are pretty much the same as elliptic curves. Well, it's an elliptic curve plus a choice of point of order n. But it will be, the most important part will be elliptic curve. So what we know now is that, well, because now recall what our problem is. So we have these two polygons in the plane P, and it's the polygon P prime, which is formed by intersection points of the diagonals. And what we want to prove is that if they're projectively equivalent, then under some additional condition, P is a Poncelet polygon. And well, what we know now is that Poncelet polygons, they are associated to elliptic curves. So our main problem here will be to find an elliptic curve. So the question is, okay, we're given P and P prime, which are projectively equivalent. So the question here, well, in order to prove that they're Poncelet, we need to find an elliptic curve in this problem, because a priori there is no elliptic curve here. So our main question will be where the elliptic curve is coming from. As soon as we can find an elliptic curve in this problem, then hopefully we can prove that it's a Poncelet polygon. So the question is where the elliptic curve is coming. So are there any questions on this?
No, it's okay.
Sorry, what did he say?
No, that's perfect.
Okay, so now let's look for an elliptic curve. So I will start with explaining the general scheme of the proof, and then time permitted, I will provide some details. Well, first of all, the proof is rather long. So of course I will have to skip many details. I will just explain the main ideas. So we start with, so first of all, the very short scheme of the proof. So we start with this polygon P, about which we know that it's a fixed point for the pentagram map, that it's projectively equivalent to P prime. And from this, we should be able to construct an elliptic curve. And the first step in this is that what I show is that given this data, given this polygon P and a polygon P prime, that is formed by the diagonals and it's projectively equivalent to P. Well, in this setting implies, it allows us to construct certain commuting difference operators. So it's a rather classical setting related to integrable systems. And well, many of you may be familiar with the theory of commuting differential operators. So there is a similar theory of commuting difference operators, which of course many of you also know. It's a completely parallel theory. It's a very classical subject. And well, I'll explain that we can construct a certain algebra of commuting difference operators based on these two polygons. So it will be basically an algebraic reformulation of this geometric setting. So algebraically, this corresponds to commuting difference operators. And then, well, again, if you are familiar, say, with the theory of commuting differential operators, then you probably know that given any two commuting differential operators, you can associate an algebraic curve to those operators. And same is true for any two difference operators. And this curve, well, basically, what it describes, well, because we have two operators that commute, they have joint spectrum because they share the same eigenvectors. And we can look at this joint spectrum, and then it turns out that if we have two differential or difference operators that commute, then the eigenvalues, they must satisfy a polynomial equation. So this defines an algebraic curve, sometimes called the spectral curve, because, well, in integrable systems, it plays the role of a spectral curve. So to this thing, you can associate a spectral curve. And for general commuting difference operators, it's just a genus G curve. So it can be an algebraic curve of any genus. Well, of course, the genus can be estimated in terms of the degrees of those operators. But if the degrees are high, which is kind of the case that we'll have, then in general, we won't be able to say much more. Well, it will be a generic genus G curve. And well, the way this theory goes is that having this kind of goes in both directions. Having a curve and some additional data on that curve, one can reconstruct the operators. So, and the coefficients will be given in terms of theta functions associated with that curve. So it's very similar to integrable systems. If you know how people integrate integrable systems, they construct this spectral curve, then they have a line bundle on that curve, and then the solutions of the initial integrable system, they can be written in terms of theta functions. So this is very similar. And in fact, there are many integrable systems whose solutions can be reformulated in terms of describing certain commuting differential or difference operators, for instance, a KdV equation or, well, discrete analogs of the KdV equation. Okay, and we can, of course, apply this construction in our setting, but the crucial point is that, well, in this case, we get this algebra of commuting difference operators, and it's not arbitrary, but it's rather special. So it's a rather special algebra of commuting difference operators. It has this some special structure, and using this special structure, we can actually show that the spectral curve, in this case, it's elliptic. So we can show that the genus of this curve is equal to 1. And this step in particular, it uses that P here, it's not an arbitrary polygon, but it's a convex polygon. Because in general, if we do the same in the setting of arbitrary polygons in CP2, then we'll be able to prove using some quite basic arguments that the spectral curve will have genus at most 2. But unfortunately, it seems not possible to make this any better. So in general, we get a genus 2 curve. But if we know that the polygon is real and convex, then one can show that genus 2 is actually not allowed. So we end up with an elliptic curve. And this is what we want, because if we end up with a genus 2 curve, well, probably we won't be able to show that it's a Poncelet polygon, because Poncelet polygons, they are related to elliptic curve. So there should be some elliptic curve. And if we find a genus 2 curve, well, of course we cannot, but it seems that in that case, it will not be a Poncelet polygon. Okay, so as soon as we know that our curve is an elliptic curve, well, it's an indication that we have a Poncelet polygon. Of course, it still doesn't prove anything, because this elliptic curve is a kind of completely different from the curve in Poncelet's construction. It's coming from some commuting operators. Seems to have nothing to do with Poncelet's curve. So the way the proof goes further is, well, as I said, here we can apply this inverse spectral theory. So knowing what the curve is, now we can reconstruct our operators using theta functions on our curve. And since our curve is elliptic, well, this will be standard Riemann theta function. So this will be theta functions in genus 1. So that's an ordinary theta function. And that's basically what I do on this step. And it's kind of strange, because it seems that there should be a completely geometric proof, but unfortunately there are reasons which, time permitted, I will explain later, that I'm not able to make a completely geometric argument. So up to this point, it's geometric. So we established that the curve is elliptic, it's quite geometric, but after that I have to apply the inverse spectral transform explicitly. So it's what people do in integrable systems. In a sense, I have to, in a sense, solve. So solve means that having my elliptic curve, I use theta functions to explicitly write down. Well, this can be phrased in terms of writing down these operators. In fact, this step can be skipped. But starting from this elliptic curve, I explicitly write down the coordinates of my polygons. So I get expressions for coordinates of my polygons in terms of theta functions. And then, well, I get a bunch of formulas in theta functions, and I want to prove that it's a Poncelet polygon. Poncelet means that it satisfies certain relations. In particular, what we need to prove that these points lie on a conic, and also that there is an inscribed conic. It turns out that it's sufficient to prove just one of these things because there is certain duality involved here. And then proving this boils down to what is called Riemann relations between theta functions. It just turns out that this P being inscribed in a conic is completely equivalent to Riemann's relations between theta functions, which are known to be true. This has certain fourth order equations satisfied by theta functions, because we know they're true. They also, of course, they do have a certain geometric meaning. And using these relations, I finally proved that P is a Poncelet polygon. Because, well, I expressed explicitly its coordinates in terms of this theta function. So this is the general scheme of the proof. So now, well, let me give some details. Namely, I want, the details on this step, well, of course, we're constructing the spectral curve out of the operators. It's quite standard. There is a non-standard step when we prove that in the convex case, it's an elliptic curve. There are some tricks used there. Except for that, well, this step is quite standard. The reconstruction step is also, in a sense, standard. It's similar to standard procedure of solving an integrable system. Well, it's of course quite technical, but it's well, working with neuromorphic functions on a Riemann surface. In this field, it's pretty much what people always do if they want to solve an integrable system. So let me maybe concentrate on the first step on how we construct commuting difference operators from these two polygons. And this will also be related to the integrability of the pentagram map. So from this argument, one can also deduce that it's an integrable system. So I want to talk in more detail about this step. So I'm sorry, can we just make a break for maybe 2 minutes? Would that be okay?
As you like, surely.
Okay, I'll just get some water and we'll continue in a couple of minutes. Is that okay?
Okay, okay.
Thanks.
Anton, may I ask you just a short question?
Sure, go ahead.
There is a Lux pair for pentagram map for
Yes.
two different operators.
Yes.
And actually, is it true that the commuting operators you are talking about are just these two because of
Not quite.
dynamics, or what you should do?
So yeah, well, the answer is, well, I will actually explain this a little bit later, but if we are in a general setting for a general polygon, of course, there is also a spectral curve coming from the Lux pair. And well, that curve is, as will be seen further, that curve also corresponds to two commuting operators, but they're not exactly different. One of them is just the nth power of a shift, so it's a difference operator, and the second one is a pseudo difference operator. It's actually a ratio of two difference operators. We are now in a more restrictive setting, and in this more restrictive setting, this algebra that we'll have, it's actually generated by 3 operators instead of 2, and they will be genuine difference operators. But of course, that standard pentagram map algebra, it's contained as a subalgebra.
Okay.
So,
what you are saying that in addition to 2 Lux operators for pentagram map, there is some third operator which commutes with these 2.
That's right. And also on the spectral curve, instead of, well, usually on the spectral curve, we have 2 functions. And here on the spectral curve, because we have the 3 operators, we'll have 3 functions coming from these operators. And in particular, this is the structure that allows to show quite easily that the genus is at most 2. As I said, in fact, it turns out that the genus is 1, but for that one needs some more sophisticated analysis. But genus 2 is simple, and that basically follows from the existence of 3 meromorphic functions with a certain degree, with certain number of zeros and poles. So
Stated in another way, what you are saying, that the ring of commuting operators generated by 2 Lux operators is not maximal. What you are doing, you are finding.
exactly.
Okay.
So if you just look at 2 operators, you look at the curve will be, it will have a lot of singular points. And then you are adding this third generator that resolves those singularities, and you end up with an elliptic curve.
Okay. Thank you.
Yes. But of course, it's true, of course, the way I explained it is that this curve comes from this commuting operators. We could do it differently. We could start with a Lux pair for the pentagram map. We could consider just that spectral curve, but then we would still need these commuting operators because we want to show that there is more structure on that curve. But of course, it's possible to construct that curve just based on the Lux representation. It's the same curve. It's just a different algebraic equation describing that curve, but as a Riemann surface, it's the same curve. but we need a way to prove that this curve has small geoms. That's it.
Thank you.
So does that answer your question?
Yes, I would rather wondering where the third operator comes from.
Yeah,
Two
I will.
are obvious. Two are obvious. They're just from the beginning, from the pentagram map.
Yes, that's
And
right.
the fact that this is stationary point for the pentagram.
Well,
So,
it's pretty much the fact that it's stationary. Well, yeah, okay. So I will talk about this now. So, okay. So, can we proceed?
Sorry, Anton. Can I ask also a question about this
Sure.
Poncelet constraint? Say, is it possible to make the conclusion that this curve is exactly what do you need from this constraint, determinantal constraint, which describe the Poncelet Polygons?
It's not exactly the same curve. I think one of them is 4-to-1 covering of the other, but they are related. Yeah.
Mm-hmm. Thank you.
I don't remember which one, but they cover each other. But yes, they are close.
Yeah, but this constraint in the determinantal form is quite nice, and it is in terms of cofactors of some Cayley matrix, and well, it might be useful. No,
I don't know. I don't know.
Thank you.
Maybe. I mean, I don't know. The problem is that initially we don't know that we have a Poncelet polygon, so we just kind of we don't have any conics at all. We need to construct them somehow.
There is a nice Hitchin paper about the Poncelet and Poncelet Polygons, and
yes,
you can find these formulas there.
No, I know. No, I know what you're talking about. I know. I don't know if it can be useful in the problem that we're studying, but I know the paper. Yeah, thanks. Any other questions? Okay, so let me explain where this commuting operator is coming from, and I'll also, on the way, I'll explain the integrability of the pentagram map. So probably my approach to that is it's slightly different from what was known before, because, well, in that basically, well, there is a Log-sphere of the pentagram map due to Solovyov, and what I will construct is a different Log-sphere. So it's a kind of dual to his, and this will be more convenient for our purposes. But of course, as usual, one can show that the spectral curve is the same. So the spectral curve one gets from different Lax representations. It's the same curve. So let me explain what all of this has to do with difference operators and where these operators come from. Well, the first observation, which is very well known, is that, well, if we have a polygon in the plane, then, well, it's a polygon in the projective plane, then this can be encoded by a difference operator, and this is done in the following way. So we regard the vertices of the polygon as a sequence of points in P2, and we will assume that it's an infinite sequence, but it's n-periodic. So it's just an alternative point of view on polygons. So it's an n-periodic sequence of points in P2, and then we can lift every such vertex to R3. So we basically take homogeneous coordinates of every point, and we do it in an arbitrary way. It's not unique. So we lift those points, the sequence, this periodic sequence of points, to a periodic sequence of vectors in R3. And, well, actually, let me write it as, instead of using subindices, I'll write this as functions. So this will be, we are thinking about functions from Z to P2. This will be a little bit more convenient notation. And and then here we get a function from Z to R3, and then so we get this sequence of vectors. And the way we can describe this sequence of vectors, well, if we take 4 consecutive vectors, v of I plus 1, v of I plus 2, and v of I plus 3, then since they're all in R3, there is, of course, a linear relation between them. So we can write down this linear relation, a relation like this, and the coefficients, they will be certain periodic functions A, B, C, and D. These are again Z functions on Z, which are valued in real numbers. So A, B, and C, and D, they are all functions from Z to R, and they are n-periodic. So, and this equation is just an alternative way to describe this vectors. We describe vectors in R3 by explaining what the linear relations between them are. And this, one can recover the vectors from the description up to a simultaneous linear transformation. So, and
Anton, excuse me, Anton,
yes.
you are introducing your capital V is also periodic, or you're having some?
Yeah, it is periodic. Yes, it's a periodic lift of a periodic function. Capital V is periodic. Yes.
Anton, excuse me, there is a restriction. There is a restriction. N is not a multiple of 3.
No, I don't care about that. So, because I'm not saying that. Well, what people do is sometimes they normalize this coefficients. This is what you do in your paper. Since I'm not doing that, there is no such restriction.
Oh, I see. I see. Thank you. Thank you. Thank you.
Yeah. So as yes, A, B, and C, and D are periodic functions. So they're functions from Z to R, and they're n-periodic. And as Vale indicates, this A, B, and C, and D, they're not unique simply because, well, here the choice of this lift, it's not unique. But also here, well, the choice of the equation is also not unique because you can multiply the whole equation by any function of I. So there is a lot of ambiguity here, and sometimes one can use this ambiguity to make A and D to be equal to 1. But for that, one needs a restriction that n is not divisible by 3. But since we will not be doing that, then we don't have any restrictions on that. So what I was going to say is that one can rewrite this equation here. So what is written here is that a certain linear operator acting on the function v is equal to 0. So what is written is that dv is equal to 0. And what this operator d is, so d is the following operator. So the first term here is we just multiply v of I by a function a of I. So it's basically a scalar operator. It's an operator that multiplies by a function. So it's a of I. And the next operator, it's b of I, but we also have a shift operator involved here. So it's v of I plus 1. So we have a certain left shift. So we'll write it as b of I multiplied by t, where t is a left shift operator. Okay, so we have a of I plus b of I t plus c of I t squared, because that corresponds to our third term. And finally, the last term is d of I t cubed. So, and this is an operator acting on functions on Z, and well, we consider everything in the periodic setting. So here, the coefficients of this operator are periodic. So this is, we can call this n-periodic difference operator of order 3, because, well, the highest power of t, which is involved in this operator, is 3. And as I said, one can encode polygons by such operators. And there are 2 remarks here that should be made. Well, first of all, the first thing is that the correspondence between polygons and operators, it's not one-to-one, in particular because, as I said, well, here, this v of I, it can be multiplied by an arbitrary function of I. And also the equation here, it can also be multiplied by an arbitrary function, well, by periodic function. And because of that, well, multiplying v by a function of I is, in terms of this equation, dv is 0, it means that we multiply d by the inverse of that function from the right. And then multiplying these equations here by some scalars means that we can also multiply d by a scalar function from the left. So what all this means is that d is defined up to transformations of the form alpha d beta inverse, where alpha and beta, they're scalar operators. So they are operators of multiplications by functions. These are alpha of I and beta of I. One can also observe that alpha and beta, they don't really have to be, they don't have to be periodic. Of course, if they are both periodic, then we're good. So this is a well-defined action. But they can also be quasi-periodic. It's fine that if when we shift by n, then there is a certain monodromy z. So we can allow alpha of I plus n be z times alpha of I, but this z should be the same for alpha and beta. So alpha and beta should be scalar quasi-periodic operators with the same monodromy. And such operators, well, the invertible ones, they form a group, and we need to consider third order difference operators up to this group action. So this replaces the normalization. So instead of saying that let two coefficients be 1, we just consider operators up to this action. Well, of course, if n is not divisible by 3, it's a kind of the same thing, because this action has a section given by two coefficients being 1, but the quotient representation will be much more convenient for our purposes. So now we see that we should consider difference operators up to this action. And then, well, the space of difference operators up to this action is in one-to-one correspondence with polygons. But again, there is a remark here. Well, how do we reconstruct polygon from a difference operator? We just solve this equation, dv is 0. So basically, dv is 0, this equation, it's an infinite sequence of recurrence relations from which we reconstruct the polygon. It's easy to see that the polygon does not depend on the choice of d in its equivalence class. But the problem that we get is that when we solve recurrence relations with periodic coefficients, in general, we don't get a periodic solution. So it's similar to differential equations. If you solve a linear ODE with periodic coefficients, solution is not periodic. It's only quasi-periodic. You have a certain monodromy. Same problem here. So these polygons, which one obtains in general, these are polygons with monodromy. So they're not really closed, but they're only closed up to a certain projective transformation. So it's a kind of thing when you go around, you only close up after a projective transformation. These are also known as twisted polygons. So this will not really be an issue for the argument I'm going to make, but it should be remarked that, well, there is a one-to-one correspondence between the space of third order periodic difference operators with this action and this twisted polygons with monodromy. Okay, so now I need to explain how this is related to the pentagram map and how one can use this to obtain a lax representation for the pentagram. So let's consider the following problem. So we have this space of polygons, and the pentagram map acts on the space of polygons. And now we have the space of difference operators. And as we just discussed, well, it's third order difference operators in the periodic. As we just discussed, the space of polygons is a quotient of the space of difference operators. And because of that, there is a projection from difference operators to polygons. And using that projection, okay, we have a pentagram map acting downwards. Using this projection, we want to pull back the map upwards. So we want to lift the pentagram map to difference operators. Well, of course, because it's a projection, when we lift a map, we're no longer gonna get a map because, well, it's a pullback of a map by a projection. Instead of a map, it's gonna give us a multi-valued map or a correspondence. So here, we're gonna get a correspondence on the left because there are many difference operators corresponding to the same polygon. On the level of difference operators, the pentagram map, it's no longer a map, but it's a correspondence. And it turns out that this correspondence is of a very simple form. So in terms of difference operators, the pentagram map, it's a very simple thing. And this observation will imply the lax representation and everything else that we. So namely, let's look once again at our difference operator D that encodes the polygon, and it has the form A plus BT plus CT squared plus DT cubed. And well, what I'm gonna do, I'm gonna break this operator into two parts. So one part is gonna be A plus CT squared, and let's call this D plus. So D plus is A plus CT squared, and D minus is BT plus DT cubed. And it should be already clear that this has something to do with the pentagram map because this is kind of shift by 0, shift by 2. So this corresponds to taking a diagonal in the polygon. This is shift by 1, shift by 3. So this is taking another diagonal. So this operators, it's natural to consider them if we're looking at the pentagram. And now the claim. So, well, as I said, the pentagram map on the level of difference operators, it's gonna be a map from D to D tilde, and this map is actually a multi-valued map. It's a correspondence, so it's a certain relation between D and D tilde. And in order to describe this map, instead of D and D tilde, I will use the positive and negative parts as I define them. So I will describe a correspondence between D plus D minus and D plus tilde D minus T. And it turns out that in these terms, the pentagram map is a very simple relation. So the pentagram map is the following equation. So it's the equation D plus tilde multiplied by D minus is equal to D minus tilde D plus. So the claim is that the pentagram map is this very simple relation between difference operators. And before I explain why this is true, let me say that this almost immediately implies lax representation for the pentagram map, because this relation here can be rewritten in the following form, can be rewritten by saying that D minus tilde inverse D plus tilde is equal to D plus D minus inverse. So it's just an obvious way to rewrite this equation. It does, of course, involve inverting certain difference operators. So these are now no longer difference operators, but they're pseudo-difference operators. If you don't like pseudo-difference operators, well, there is an isomorphism of the algebra of difference operators with the algebra of Laurent polynomials with values in matrices. So here in this equation, one can think about the loop algebra instead of difference operators, and then it's easy to invert things in the loop algebra. So rewriting this equation like this, so we get this relation, and if you look at this relation, then, well, basically the thing on the left is related to the thing on the right by swapping factors. So that is a refactorization relation, and this immediately implies that the pentagram map has a lax representation, because what this thing is saying, it's saying that the pentagram map, if we consider the operator D minus inverse d plus, then the pentagram map sends this to d plus d minus. So this is just exactly what is written here. So in other words, in terms of this operator, if we call this L, then L under the pentagram map, L changes as d plus L d plus inverse. So this is a lax representation for the pentagram map. And from this one can deduce that this map is an integrable system, because if you consider the representation of difference operators in the loop algebra, then this becomes a lax representation with spectral parameter. This gives a spectral curve and all necessary stuff to establish the integrability of this. So the only thing that we made.
Anton, how you put spectral parameter in these operators? Because it's,
okay, so the spectral parameter, it's naturally there, because if you think about this algebra of n-periodic difference operators, well, every n-periodic different operator, it commutes with t to the power of n. So we already have two commuting operators here. So there is a spectral parameter just because of that. Or another way to think about this is that, well, any n-periodic difference operator, it acts on the space of sequences. Of course, it acts on periodic sequences of real numbers, but it also acts on sequences of real numbers with the property that xi plus n is equal to zxi. So for every z, we get a representation of this algebra. So it's a family of representations, which actually identifies n-periodic difference operators with the algebra GLN tensor with with Laurent polynomial. So this algebra of n-periodic difference operators, it's isomorphic to Laurent polynomials with coefficients in GLN. And it's because we consider periodic operators. They already commute with the nth power of the shift.
okay, so this is the different spectral parameter then considered by Solovyov.
Well, as I said, this lax representation is in a sense dual to his. So what this means is that, okay, if you have a lax representation with a parameter, then you form the spectral curve. On the spectral curve, you have two variables. One is your spectral parameter, and the other one is the eigenvalue of your map. If one considers his curve and my curve, then the role of these two variables, they are just interchanged. So his eigenvalue becomes my spectral parameter, and my eigenvalue becomes his spectral parameter. So it's a kind of a common situation in integrable systems that you have two lax representations coming from two different projections of the spectral curve. Right? So this is what's happening. So,
but then it should be different from the spectral parameter in the work of Tabachnikov, of Sienko.
No, it's no, because theirs is related to furthers by a certain gauge transformation.
Okay.
So it's not different. It's related by a gauge transformation. Okay, so coming back to our problem. Okay, so I still need to explain why the pentagram map corresponds to this equation. This is a kind of the main point in the proof, and it's pretty simple. So I want to show, okay, this is a certain relation on difference operators. I want to explain that on the level of polygons, this is the pentagram. So recall that the relation between operators and polygons is through the equation dv is 0, where d is d plus d minus. So, well, v is of course a sequence of vectors. Then we project it down to the projective space. We get a sequence of points. That's our point. So let's use this relation dv is 0 in our equation. Well, because dv is 0, we have that d plus v is equal to d minus v with a negative sign. So now consider this equation on difference operators and apply both sides of this equation to V. So if we do that, we get that d plus tilde d minus V is equal to d minus tilde d plus V, but we know that d plus V is negative d minus V. So moving things to the left, here we have d minus V, here we have d minus V, so it means that we can group this and this. So as a result, we obtain that d tilde applied to d minus V is equal to 0. So that's what we get from this equation here. And this is telling us what this operator d tilde is, because, well, d tilde annihilates d minus V. So this means that in terms, so for polygons, our map, this is a multi-valued map on difference operators. On the level of polygons, this map acts as follows. V goes to d minus. So this is our map on the level of polygons. And now it's easy to see that this is exactly the pentagram map. Because, well, recall what is d minus V. So d was an operator of this form a plus bt plus ct squared plus dt cubed. And d minus is as bt plus dt cubed part. So if we apply d minus to V, well, this will involve shift by 1 and shift by 3. So this is an infinite sequence of vectors, which is obtained from V by shifting by 1 and shifting by 3 and then combining these things. This means that if we take the ith vector in this sequence, this belongs to the span of Vi and Vi plus 3, just because of the form of the operator d minus, right? On the other hand, we know that d minus V is equal to negative d plus, and applying the same argument for d plus, we see that it belongs to, because d plus is this term plus this term, d plus V belongs to the span of Vi plus, oh, sorry, here this should be Vi plus 1, if there was a shift by 1. And d plus V belongs to the span of Vi and Vi plus. So what this means is that d minus V, it belongs to both of these spans. So it's the intersection of two spans. But the intersection of these two spans, it's exactly the pentagram map, just by definition. So it's exact, because this span on the level of the projective plane, it's a diagonal joining the vertex Vi plus 1 with Vi plus 3. And this is the diagonal joining Vi and Vi plus. So up to shift of indices, this is exactly the pentagram. So, well, of course, these indices, they are important, but roughly speaking, well, up to this shift, we see that our equation on difference operators is exactly the same as the pentagram. This by the way, can also be easily generalized to various multidimensional pentagram maps, because here in this argument, I don't really use the specific form of the diagonals I intersect. So considering higher order difference operators, we could do the same thing for various multidimensional versions. Okay, so now we've realized that the pentagram map in terms of difference operators is this equation. So now we assume that we have, and as I said, what this implies, well, that this implies the lax form for the pentagram map. So, and the lax operator is this pseudo-difference operator, and it's a periodic pseudo-difference operator, so it can be used with e to the power of n. So this is the two operators we have in general, but now we have this very special setting of having a fixed form. So now let's talk about that. So now we know that we have a point fixed by pentagram map. Was there a question? George, did you have a question?
I'm sorry, just it's my kind of look. Sorry.
Okay, fine. So in this setting, when we have a point fixed by the pentagram map, well, in that case, we can assume that d and d tilde are the same opposite, because, well, the pentagram map is the identity. It doesn't exactly mean that nothing happens on the level of difference operators, because there are many operators corresponding to one polygon, but it can always be arranged, and d tilde are the same if the pentagram map fixes the given polygon. So in that case, this equation above becomes d plus d minus is d minus d plus. So we see that this difference operator is commute, and this is where additional commuting operator is coming from. So now we have.
I'm sorry. Do you need to shift the indices as well?
Yeah,
I mean, when you do this fixed point.
That is true, because recall that we had this convention that if when we have a polygon, when we apply a pentagram map, if this is I, then the opposite point should be I prime. So this is a kind of important.
Yeah,
we use this labeling. So because of this convention, the operators we get, they will be of the following form. So one operator. So the way I wrote them, one of them was contained a scalar function and shift by 2, and another one was t and t cubed. So what? In view of this convention, these operators will actually be of the following form. So d plus is a times t. So recall that n is an odd number. It's a number of vertices. So d is a times t to the power of n minus 3 over 2 plus t to the power of n plus 1 over 2. Well, d minus is of the form b t n minus 1 over 2 plus d n plus 3 over 2. So it's, well, in particular, this labeling, it allows to make things symmetric. So because before the form of d plus and d minus, they were kind of non-symmetric, but now, well, in particular, one can notice is that if we take the adjoint of the operator d plus, then it will have the same form as d minus. And this is actually one of the steps in the proof that one shows that these operators, they actually have to be adjoint to each other. So what we end up with is a very special algebra of commuting difference operators. So we have two operators of this form, and in addition, both of them commute with t to the power of n because they are periodic. And then using that algebra of commuting operators, we do this whole procedure that I described. We show that they correspond to an elliptic curve. And then from that elliptic curve, we reconstruct the initial polygon, and it turns out to be a Poncelet polygon. And as I said, yes?
Excuse me. So far, there was no use of convexity assumption. So you said that from that you get not the elliptic, but probably the curve of genus 2.
That's right. So first of all, to show that it's a curve of genus 2, it's easy. So namely, well, if we look at this form of d plus and d minus, we can notice that if we compose d plus with d minus, well, these indices, they add up to n. So we get an operator of order close to n, and then we can multiply it by t to the minus n, and this will be a very simple operator. It's similar to the Lax operator for the total lattice. Namely, it's basically an operator which contains just one shift to the left, one shift to the right, and a scalar function. So the algebra contains this very simple operator of order 2. And in addition to that, we can consider this operator, which is d plus d minus inverse. It's a pseudo difference operator, but in a sense, this pseudo difference operator, one can explain that it has order 3. And because our algebra contains order 2 operator and order 3 operator, from that it follows that the genus is at most 2. Basically because well, the polynomial equation relating them, it will have second order in one variable and second degree in one variable, third degree in the other variable. So it follows from that the genus can be at most 2. So this is easy, showing that the genus is 2. Now, well, the question is, how do we show that the genus is 1? Well, for that, we need more careful analysis of the algebra of meromorphic functions on that on the spectral curve. And namely, what one can show in general is the following. So recall that our polygon, it corresponds to the operator d plus d minus. So, well, if we look at this operator, this is a particular generator in our algebra. If we compute the kernel of this, this will give us our initial point. And then it turns out that in addition to that, we need to look at the operator d plus minus d minus. And what I showed is that the spectral curve may only have genus 2. So this one has have genus 2 if and only if the polygon corresponding to this operator is a closed polygon. So in other words, this operator d plus minus d minus, it should be, I don't know what's called superperiodic or monodromy free operator, which is in general not going to be the case. So only if this is monodromy free, the spectral curve may have genus 2. And this follows from, well, because this condition, of course, that it's closed, it can be expressed in terms of values of some meromorphic functions on the spectral curve. And then the way I use convexity is that I show that for convex polygons, if the polygon corresponding to the sum is closed, and moreover it's convex, then it's not possible that the polygon corresponding to the difference is also closed. So this basically follows from, well, we look at the, we can explicitly express the monodromy matrix for this d plus minus d minus. It's going to be a certain product of matrices. And it can be explicitly expressed in terms of some invariance of the initial polygon. And then we can see that in the convex case, these matrices, they have certain positivity properties, which kind of prevents the product from being the identity matrix. So using, it's some kind of a trick. I don't know any natural explanation, but one can use this trick to show that spectral curves of genus 2 are not allowed. So if we don't impose convexity, then I think these curves of genus 2 are possible. The problem is it's hard to construct an example explicitly, of course, well, because it's related to genus 2 curves. So these polygons that arise, they should, well, one can write them in terms of genus 2 theta functions, but I don't know if one can kind of make it more explicit. But using this, it's actually not the only place where I use convexity in the proof. There are quite a few places where one needs to get rid of some degenerate cases to show that these degenerate cases are not allowed. And convexity saves us from many different degeneracies. And so this is pretty much, well, how the proof goes. So I construct the special algebra of operators. I construct the spectral curve. Using this trick with positive matrices, I show that the spectral curve has genus 1. And then finally, I just reconstruct the initial polygon by writing down the vertices in terms of theta functions, and then observing that, well, this theta functions, well, these points, these coordinates given theta functions, they indeed define the Poncelet Polygons. And I will probably stop here, and let's see if there are any questions.
And here in the last part you use that the number of points is odd,
Yeah.
because otherwise it's maybe not true.
Yeah, the number of points for sure must be odd. I mean, this is, well, actually in the problem itself, because the problem is that we want the polygon to be fixed by the pentagram map. The question is, what exactly does that mean? Because when we say that it's a fixed one, we should fix some labeling. And for the odd number of vertices, we have this nice labeling drawn in this picture. So this is the labeling, I assume. But one can, of course, ask a more general question, is what are the polygons fixed by the pentagram map, like for any labeling? And but I don't think that that question has such a simple answer. So we wouldn't, one shouldn't expect that this is some nice class of polygons. But I think this is the most natural case because, well, as I said, it's the only labeling which doesn't break this left-right symmetry. And because of that, it kind of turns out that this is a natural class of polygons. But these are exactly Poncelet. One can also overcome this labeling problem if one considers the square of the pentagon. So another question is, how do we describe all polygons fixed by the square of the pentagram map? So I expect that for odd number of vertices, the answer is still the same, but for even, it probably won't work. Because, well, we know that I think hexagons, they're fixed by the square of the pentagon. Maybe fourth power. So to keep the labeling right. But hexagons are in general not Poncelet. So for even number, I guess it's a little bit different.
Anton, you said, but could you repeat just what is the possible relation of this curve of genus 2 with the desired curve of genus 1?
I don't know. I mean, I think that when it's genus 2, then it just doesn't correspond to Poncelet polygons. So it's just some more general polygons related to genus 2 curves. No, because the thing is, what I prove is that it's not a genus 2 curve, but it's a genus 1 curve. Well, I mean, from the equation, we see that it, well, if that equation was, well, because what I explained here is that if one chooses special generators in our ring of difference operators, then the equation we obtain, it will be of the form, will be of degree 2 in one variable and degree 3 in another variable. So if that defines a smooth curve, then of course it would be a genus 2. But it's kind of what I show is equivalent to saying that that curve must have a singularity. And also if one uses other generators, like if one writes the spectral curve as one usually does it for the pentagram map in the standard form. So that is if you take these two operators and you write down the equation of the spectral curve, then it will be of a very high degree. But what it means is that for Poncelet polygons, it just has a lot of singular forms. So yeah, just in the convex case, I end up with an elliptic curve. That's the point. But one needs to use kind of a few tricks to show that it's elliptic. And the question, a good question is what kind of polygons correspond to genus 2 curves? I don't know. I mean, is there any natural geometric description of that? Hard to say. I don't know.
Thank you very much. Are there any other questions?
Can you say something about periodic orbits?
That's a very good question. So, I mean, it seems like we know that in general, possibly a different approach here could be applied because we know that the pentagram map is algebraically integrable and it corresponds to a shift on the spectral curve by a certain divisor R. And if it's a fixed point, then it means that R is a principal divisor. So this gives us a new meromorphic function on the spectral curve. So I'm not exactly sure that one could reformulate my proof in that terms, because I think this would still give us genus 2 instead of genus 1. But maybe, I don't know. But the point is that this approach seems to be generalizable to periodic, because, okay, maybe now let's ask when it's period 2. Well, this means that 2R is 0. So again, we get a certain principal divisor. Again, we get a certain meromorphic function, but now 2R, this divisor contains more points. So that function is of higher degree, which means that we should probably expect higher genus. So I guess one can prove certain estimates, like if a point is of period K for Pentagram Map, then the genus of the spectral curve is bounded by something in terms of K, but I mean, it's not very geometric, right? It's still not clear what these polygons look like geometrically. But I mean, generically, the genus of the spectral curve is of order n, where n is the number of vertices. And if the point is of sufficiently small period, then, well, it's a certain restriction on the genus, but still it's kind of, well, one can probably use this to estimate dimensions of the set of periodic points, things like that. But if you want a precise answer, okay, what can I tell you? I can write you theta functions in terms of the genus K curves, but that's probably not an answer that you would want to see. I think there is some question in the chat. What is the relationship between the elliptical spectral curve and the original flat curve? So the relation is that one is the 4-to-1 cover of the other. So, but I see that a posteriori, when I reconstruct the polygon, I can explain that one of the curves covers the other one. And the second question is, how do I use the condition that the polygon is real? Well, I use it in a few places. First of all, I've already said how I use that it's convex, and of course that requires it being real because, well, I use certain properties of real positive matrices, and this will certainly not work for complex matrices, but that's not the only place. So actually, well, I just didn't provide the whole argument, but in the actual argument, it has an additional step. So I end up with proving that not the initial polygon is Poncelet, but so we have this operator d plus d minus, and we want to prove that the corresponding polygon is Poncelet. What I prove first is that there is some constant lambda such that the polygon corresponding to this is Poncelet. And then the final step is to show that lambda is 1. And for that, the real structure is important, because on that step, I already know that my curve is elliptic. And then I look at the real part of the spectral curve, which turns out to consist of 2 circles. And I have some meromorphic functions with special properties. And I show that these properties can only be arranged if this lambda is 1, otherwise. It's just some kind of a topological argument, because the real part of an elliptic curve is 2 circles, so you analyze some real functions on 2 circles. And you show that if lambda is not 1, then that arrangement of zeros and poles of that function that you get is just not possible. So reality is used in quite a few places. I mean, well, as I said, the general argument is pretty much standard, but there are a lot of different tricks I use from the way. So, yeah, okay.
Then I'd like to hear you report the third time.
All right.
I'd like to listen you report another time, another one. It's okay. Thank you very much.
Yeah,
I
thanks.
suppose
No,
we
thanks,
should
thanks
finish.
for inviting me. I don't know if I actually said thanks, but I'm very happy to give a talk for it.
Thank you very much. Thank you very much. I'd like to make a short announcement of the next talk. It will be in 2 weeks, and it will be the talk of Misha Gechtman on the Poisson side of the cluster algebra domain for this big question. So you're welcome.
Thanks.
So.